The universe is a vault of unanswered questions. We will explore 35 cosmic mysteries that still baffle the most brilliant scientific minds on our planet. By the end of this journey, you will grasp the profound enigmas shaping our understanding of reality itself. We will confront the invisible substance holding galaxies together and ask why the cosmos is utterly silent. The secrets of the stars hold the key to our own existence. What cosmic question keeps you looking up at the night sky? Our universe is held together by a ghost. Galaxies spin so fast that the gravity from their visible stars is not nearly enough to keep them from flying apart. Something invisible, something that does not emit or absorb light, must be providing the extra gravitational glue. This is the dark matter enigma. We cannot see it, but we can watch its shadowy hand at work, bending the light from distant galaxies and sculpting the largest structures in the cosmos. It is a cosmic architect we have never met. The leading suspects for this invisible substance have names that sound like science fiction. Weakly interacting massive particles, or WIMP, are hypothetical heavy particles that barely interact with normal matter. Then there are actions, incredibly light theoretical particles that could be streaming through you right now by the trillions. Finding out which one, if either, is correct is more than a particle hunt. It is about understanding the fundamental recipe of the universe. If dark matter makes up over 80% of all matter, then we are the cosmic minority, living in a world built from the exception, not the rule. Unlocking its identity would tell us what most of the universe is actually made of, and ultimately how this vast cosmic story will end. If dark matter is the ghost holding galaxies together, then dark energy is the phantom force tearing the entire cosmos apart. This is an even deeper and more perplexing mystery. For most of the 20th century, scientists believed the universe's expansion was slowing down after the Big Bang, gradually coasting against the pull of gravity. Then, in the late 1990s, two independent teams made a shocking discovery. By observing incredibly distant stellar explosions called Type 1, a supernova, they found the universe is not just expanding. Its expansion is accelerating. Something is actively pushing galaxies away from each other at a faster and faster rate. That something is what we call dark energy. It makes up a staggering 68% of the entire universe, dwarfing even dark matter. Imagine blowing up a balloon with tiny dots on it, and instead of the dots slowly spreading apart, they suddenly start racing away from each other as if the balloon were inflating with a mind of its own. That is the baffling reality of our cosmos. The leading explanation for this bizarre force goes back to Albert Einstein. He once introduced a fudge factor into his equations of gravity, a cosmological constant, to force the universe to stand still. He later called it his greatest blunder. Now it seems he might have been right for the wrong reason. This constant could represent a fixed energy density woven into the very fabric of empty space, a vacuum energy that exerts a sort of negative pressure driving the acceleration. But there is a huge problem. The predicted strength of this vacuum energy is a staggering 120 orders of magnitude stronger than what we observe. That is a 1 followed by 120 zeros. It is the worst prediction in the entire history of physics. This colossal failure has led scientists to consider a more dynamic and unsettling possibility. Perhaps dark energy is not a constant at all, but a strange, fluid-like energy field that permeates the cosmos, a concept known as quintessence. This field could change over time, potentially weakening or even reversing its effect in the far future. Is the cosmos destined for an eternal, ever faster expansion, tearing everything apart until even atoms are ripped asunder in a final big rip? Or could this phantom energy one day fade away, allowing gravity to take the wheel once more? The true identity of dark energy remains the single greatest puzzle in all of cosmology, a question that will define the ultimate fate of everything we see and know. After confronting the phantom forces shaping our cosmos, we are left with a profound silence. The universe is vast and ancient, with billions of planets that could harbor life, yet we hear nothing and see no one. This is the heart of the Fermi Paradox, a cosmic contradiction that asks a simple, haunting question. Where is everybody? The numbers alone suggest a crowded galaxy. There are more stars in the observable universe than grains of sand on every beach on Earth. A significant fraction of those stars are orbited by planets in the habitable zone, where temperatures are just right for liquid water, the solvent of life as we know it. Given so many chances, life should have arisen many times over, so why does the sky appear so empty? One chilling resolution is the Great Filter hypothesis. This idea suggests that there is some kind of barrier, a near impossible step, that prevents life from advancing to a stage where it can colonize the stars. This filter could lie in our past. Perhaps the spontaneous emergence of life from non-living chemistry is extraordinarily rare, or it could lie ominously in our future. Maybe every advanced civilization eventually creates the technology that leads to its own destruction, whether through environmental collapse, artificial intelligence, or some other unforeseen catastrophe. If this is true, then our own continued existence is no guarantee. Another possibility is that we are simply not listening correctly, or that we are hopelessly primitive. An advanced civilization might not use radio waves, the technology we currently scour the skies for. They could communicate through means we cannot yet conceive of, like manipulating neutrino streams or gravitational waves. Their artifacts might be all around us, so advanced that they are indistinguishable from the natural world. Or perhaps spacefaring life is out there, but it has no more interest in communicating with us than we have in communicating with a single ant on a forest floor. The distances between stars are also unimaginably vast. A signal from a civilization in a nearby galaxy could take millions of years to reach us, and by the time it arrives, that civilization may have long since vanished. We are like a brief flicker of a candle in a cathedral, hoping another candle is flickering at the exact same moment, in the exact same corner of an impossibly large and dark room. The silence is not an answer, but a question in itself. Are we the first, the last, or simply alone in a universe of untapped potential? This profound silence might not be a sign of emptiness, but one of deliberate choice. The zoo hypothesis offers a startling answer to the Fermi paradox. It suggests that advanced galactic civilizations are fully aware of our presence, but they are intentionally hiding from us. Think of it as a cosmic wildlife preserve where humanity is the protected species, left to evolve and develop without outside interference. Perhaps there is a universal ethical code, a prime directive of sorts, that forbids contact with emerging intelligences until they reach a certain technological or moral maturity. The universe could be a bustling galactic community, and we are simply living in a quiet, cordoned-off section, blissfully unaware of the conversation happening just beyond the fence. Our planet might be a designated library or a museum, a living record of a primitive civilization, observed for study but not for interaction. This idea transforms our search for alien life. If the zoo hypothesis is correct, then our efforts to listen for radio signals are futile, because the advanced societies are actively jamming our frequencies or using communication technologies we cannot perceive. Our most powerful telescopes might be looking at a carefully curated show. This raises a deeply philosophical question. If we are in a zoo, who are the zookeepers, and what are the rules for graduation? Does a civilization earn its place among the stars by achieving sustainable energy, or by overcoming its own self-destructive tendencies? The ongoing search for extraterrestrial intelligence, or SETI, continues to scan the heavens for any whisper of a signal that might have slipped through this hypothetical quarantine. Every silent hour of observation is a test of this grand hypothesis. Are we truly alone, or are we being given the precious, silent gift of time to grow up? This cosmic silence could be hiding a deeper conflict, one that plays out in the most extreme environments the universe can offer. Deep within the warped space around a black hole lies a paradox that threatens to unravel our understanding of reality itself. The black hole information paradox pits two pillars of modern physics against each other in a fundamental and irreconcilable way. On one side, we have Einstein's general relativity, which describes black holes as simple, voracious objects. They possess only three properties: mass, spin, and electric charge. According to this classical view, if you were to throw a grand piano, a library of books, and a million unsolved crossword puzzles into a black hole, all the intricate information contained within those objects would be utterly and permanently erased from our universe. The black hole would simply become a little more massive, swallowing the unique identity of everything it consumes. It is the ultimate shredder, yet on the other side we have the unyielding laws of quantum mechanics. Quantum theory insists that information can never be truly destroyed. It can be scrambled, hidden, or transformed into an incredibly complex form, but it must, in principle, be recoverable. The universe, according to quantum rules, must keep a perfect, permanent record of its past. So, which is it? Is information lost forever in a black hole's depths, or is it somehow preserved? This is not just a philosophical debate. The integrity of all physics hangs in the balance. The legendary Stephen Hawking first brought this conflict to a head. He calculated that black holes are not completely black. They slowly leak radiation, now known as Hawking radiation, and over eons they can evaporate completely. But here is the catch. Hawking initially showed that this escaping radiation is entirely random, carrying no information about what fell in. If the black hole evaporates and disappears, the information it consumed vanishes with it, violating a core principle of quantum mechanics. Hawking famously bet that information was indeed lost, a bet he later conceded as the physics community sought a way out of this crisis. Modern theories have proposed breathtaking solutions. One idea is black hole complementarity, which suggests that from the perspective of an outside observer, information never actually crosses the event horizon. Instead, it is smeared and encoded onto the black hole's surface, while from the perspective of an object falling in, it passes through the horizon none the wiser. Both perspectives are correct in their own frame, resolving the paradox by stating that no single observer ever witnesses the destruction of information. This leads to an even more profound concept, the holographic principle. It proposes that our three-dimensional reality, including everything that falls into a black hole, might be nothing more than a projection of information stored on a distant, two-dimensional surface, like a cosmic DVD encoding a three-dimensional movie. The black hole's event horizon could be that surface, a vast, pixelated screen holding all the data of what lies within. In this view, the information of your grand piano and library is not lost. It is just painted onto the boundary of the black hole in a language we do not yet understand. The paradox forces us to ask what reality truly is. Is the universe fundamentally made of stuff, or is it made of information? The answer, hidden behind the veil of a black hole's shadow, might rewrite the very definition of existence. While we grapple with the nature of reality inside black holes, our own planet is constantly bombarded by fragments of cosmic violence. Ultra-high energy cosmic rays are subatomic bullets, protons, and atomic nuclei that slam into Earth's atmosphere with unimaginable force. A single one of these particles can carry the energy of a professionally thrown baseball, all compressed into a speck smaller than an atom. This means they are millions of times more powerful than anything we can create in our largest particle colliders. They are the universe's natural superaccelerators, and we have almost no idea what cosmic engines are capable of launching them at such incredible speeds. The mystery is not just their immense power, but their elusive origin story. These particles are electrically charged, which means they do not travel in straight lines. As they journey across the cosmos, the tangled magnetic fields that fill the space between galaxies act like a hall of mirrors, bending and twisting their paths beyond recognition. By the time one of these cosmic rays reaches our detectors, it is impossible to simply look back along its route and see where it came from. It is like trying to find the source of a single, ricocheting bullet in a vast, pitch-black maze. So what cosmic phenomena are capable of such staggering feats of power? The leading suspects are some of the most violent objects in the universe. Active galactic nuclei, the supermassive black holes at the hearts of distant galaxies, are prime candidates. As these monstrous entities devour surrounding gas, they can eject jets of material stretching for thousands of light years, potentially acting as natural particle accelerators on a galactic scale. Another possibility lies in the aftermath of stellar cataclysms. The shock waves from supernova explosions could, in theory, accelerate particles to these extreme energies over vast distances. Yet, for the very highest energy cosmic rays we have observed, even these tremendous events might not be powerful enough. This has led scientists to consider even more exotic sources, perhaps phenomena that involve physics beyond our current standard model. Could they be produced by the decay of hypothetical super-heavy dark matter particles from the early universe? Or are they the signature of cosmic strings, defects in the fabric of space-time itself? Each ultra-high energy cosmic ray that strikes our atmosphere is a cryptic message, a calling card from the most energetic processes in the cosmos. The problem is that the message is scrambled and we are still learning how to read it. Unlocking their origins would not just tell us where they come from. It would open a window into the fundamental forces operating at energy regimes we can only dream of recreating on Earth. Sometimes the biggest secrets are hidden in the smallest of deviations. As the Pioneer 10 and Pioneer 11 spacecraft journeyed beyond the outer planets, scientists tracking their trajectories noticed something peculiar. The probes were slowing down just a little bit more than anyone had predicted. This tiny, persistent deceleration became known as the Pioneer Anomaly. It was a minuscule effect equivalent to a 10 billionth of a G, a force so small it would barely nudge a feather. Yet for decades, this faint whisper from the void challenged our understanding of the solar system. Could it be a sign of new physics, perhaps a flaw in Einstein's theory of gravity itself? Some theorists proposed that our model of gravity needed a slight tweak at the vast scales of the solar system, an unseen force manifesting only in the deep cold of interstellar space. Others wondered if it was evidence of something more exotic, like the gravitational pull of unseen dark matter clustered around our sun. The anomaly became a classic scientific detective story, a puzzle box with the simplest of exteriors hiding profound possibilities. The eventual culprit, however, turned out to be far more mundane, yet brilliantly insightful. After years of meticulous analysis, a team of researchers realized the answer was thermal recoil. The spacecraft's nuclear power sources generated heat, and as that heat radiated away from the spacecraft in the form of infrared light, it created a tiny, imbalanced push. Picture a simple garden sprinkler where water shooting out one direction makes the sprinkler head spin the other way. In the vacuum of space, the Pioneer probes were like that sprinkler, with heat photons acting as the water, providing a constant, faint thrust that ever so gently applied the brakes. This explanation, confirmed through exhaustive computer modeling that traced the complex paths of heat across the spacecraft bodies, has largely settled the debate. The Pioneer Anomaly teaches us a humbling and powerful lesson. It shows how our hunger for monumental discovery must always be tempered by relentless attention to detail. A ghost in the machine was not a new law of the universe, but the quiet, predictable consequence of engineering we had simply overlooked. It proves that even when searching for cosmic monsters, we must first account for the tiny whispers. From the faint whispers of spacecraft to the ultimate question of cosmic destiny, we arrive at the grandest mystery of all: how will the universe end? The answer is written in the subtle interplay between the outward push of dark energy and the inward pull of gravity, a cosmic tug-of-war whose outcome is still undecided. Scientists have outlined three primary and dramatically different scenarios for the final act, each hinging on the universe's precise density and the true nature of the dark energy that drives it. The first and currently most favored scenario is the Big Freeze, also known as heat death. In this future, the expansion of the universe continues to accelerate, driven by dark energy, until the cosmos becomes a vast, cold, and unimaginably lonely place. Galaxies will recede from one another, their light stretched into invisibility. Stars will burn through their fuel and die one by one until no new stars are born. Over trillions upon trillions of years, even black holes will evaporate via Hawking radiation. The universe will approach a state of perfect equilibrium, a lukewarm bath where no energy can be transferred, no work can be done, and no complex structures can exist. It is not a dramatic explosion, but a slow, quiet fading of all light and life into eternal, maximum entropy. The second possibility is far more violent and sudden, the Big Rip. This scenario requires that dark energy, in the form of something called phantom energy, grows stronger over time. If this happens, the accelerating expansion would not just continue, it would intensify beyond all bounds. First, galaxy clusters would be torn apart, then individual galaxies. As the end draws near, the phantom energy would overcome the gravity holding stars together, shredding solar systems. In the final moments, it would grow so powerful that it would rip apart planets, then molecules, and finally, the very atoms and subatomic particles that constitute all matter. The fabric of spacetime itself would be torn asunder in a catastrophic final instant. The third, and now considered less likely, scenario is the Big Crunch. This is the classic cyclical universe model. It proposes that the density of matter and energy in the cosmos is high enough that gravity will eventually halt and reverse the expansion. After reaching a maximum size, the universe would begin to contract. Galaxies would start rushing back toward each other, the cosmic background radiation would heat up, and the sky would glow with increasing intensity. The end would be the mirror image of the beginning, all matter and energy collapsing back into an infinitely hot, dense singularity, a potential rebirth point for another Big Bang. So, which fate is ours? The answer lies in ongoing, painstaking measurements of the cosmos. Astronomers are using telescopes to chart the expansion rate with ever greater precision, observing distant supernova and mapping the large-scale structure of the universe to weigh the cosmic content. They are trying to pin down the equation of state of dark energy, a key number that tells us whether it is a constant or a phantom force that strengthens. Every new data point is a vote for one of these cosmic destinies. We are living in the brief sliver of cosmic time, the golden hour of a universe that is still vibrant and full of light. Yet we hold the unique ability to peer into the deep darkness and ask with scientific rigor how the final story will be written. Yet even as we chart the universe's ultimate fate, a ghostly pattern in its first light hints that our most basic assumptions might be wrong. This is the mystery of the axis of evil, a name that evokes a cosmic conspiracy lurking within the afterglow of the Big Bang itself. That afterglow is the cosmic microwave background radiation, a fossilized snapshot of the universe when it was just 380,000 years old. This radiation should be almost perfectly uniform, a final echo of a hot, dense beginning. According to the foundational cosmological principle, the universe on the largest scale should have no preferred direction or special place. It should be isotropic, looking the same in every direction. But when scientists created incredibly precise maps of this cosmic background, they found something unsettling. There appears to be a strange alignment, a preferred axis that seems to connect the plane of our own solar system with the overall distribution of hot and cold spots in the ancient universe. It is as if the universe has a subtle equator and we are curiously aligned with it. This alignment, dubbed the axis of evil, is a direct challenge to the cosmological principle. If the universe has a preferred direction, then we are not in a random, average place. This would be a revolution in cosmology, forcing us to reconsider everything from the Big Bang to our own position in the cosmos. So is this axis a real feature of the universe or just a trick of the data? Skeptics argue it is a statistical fluke. When you look at any large set of data, you can sometimes find seemingly strange patterns purely by chance. It is like finding a face in the clouds. The pattern is not really there. It is just your brain imposing order on randomness. Others wonder if it is an artifact of our measurements, a subtle contamination from our own galaxy's light, or an imperfection in how we subtract its foreground glow from the deeper cosmic signal. But if it is real, the implications are staggering. It could point to a pre-Big Bang geometry that imprinted itself on the newborn cosmos. Some theories even suggest our universe collided with another universe in the multiverse during its earliest moments, leaving a bruise on the sky. Or perhaps the fabric of space-time itself is not uniform, but has a crystalline structure on scales so vast we are only now glimpsing its edges. The axis of evil remains one of the most controversial and profound puzzles in modern cosmology. It is a whisper from the dawn of time, suggesting that the universe might not be the simple, random expanse we thought it was, but something far more strange and structured. Deep within the ancient stars of our galaxy lies a chemical fossil, a relic from the first few minutes of the universe. The Big Bang was not just an explosion of space, but a forge of fundamental elements, a process called Big Bang nucleosynthesis. In those initial fiery moments, protons and neutrons fused to create the universe's first hydrogen, helium, and a tiny, trace amount of lithium. Our theoretical models of this process are exquisitely precise, predicting exactly how much of each element should have been made. For hydrogen and helium, the predictions match the observed abundances in the oldest stars almost perfectly, but for lithium, the numbers are catastrophically wrong. The oldest stars in the Milky Way, which formed from the pristine, uncontaminated gas of the early cosmos, contain only about 1/3 of the lithium that our models say should be there. It is as if a cosmic accountant discovered that 1/3 of a fundamental ingredient had simply vanished from the universe's ledger moments after its creation. This is the lithium problem, a small discrepancy with enormous implications, suggesting a fundamental flaw in our understanding of the universe's first moments. Where did all the lithium go? One possibility is that our understanding of stellar physics is incomplete. Perhaps these ancient stars have some unknown internal process that slowly destroys lithium over their long lifetimes, like a deep nuclear furnace that burns away the primordial trace. Astronomers have searched for such mechanisms, but finding one that destroys just the right amount of lithium without affecting other elements has proven incredibly difficult. The other, more thrilling possibility is that the flaw lies not in the stars, but in the Big Bang model itself. Could there be unknown particles or forces at play during those first few minutes? Some theorists propose that the presence of exotic particles, like certain types of dark matter, could have altered the nuclear reactions, reducing the final lithium yield. Others suggest our models of the particle zoo need revision, that perhaps neutrons were slightly less stable in the primordial soup than we currently believe. Each potential solution opens a door to new physics, a glimpse beyond our standard models. The lithium problem is a quiet but persistent alarm bell. It tells us that for all the majestic success of the Big Bang theory, a piece of the puzzle is still missing, a secret still held by the oldest suns in the sky. Even the universe's most fundamental number, its rate of expansion, is now a subject of fierce debate. This is the Hubble Tension, a crack in the foundation of modern cosmology. At its heart is a simple but critical question: how fast is the cosmos flying apart? For decades, astronomers have pursued two distinct paths to find this number, known as the Hubble constant. One path looks back to the infant universe, using the pristine snapshot of the cosmic microwave background. The subtle patterns in this ancient light allow scientists to calculate the universe's initial expansion rate, and then use our standard model of cosmology to predict what that rate should be today. This is like calculating how fast a teenager should be driving based on a baby picture and a known growth chart. The other path measures the universe directly in our cosmic neighborhood. Astronomers use celestial mile markers like pulsing Cepheid variable stars and cataclysmic supernova to gauge distances to nearby galaxies and measure their speed of recession. This is like using a radar gun to clock the speed of that same teenager driving down the street. The problem is that these two methods, the baby picture and the radar gun, no longer agree. The local measurements consistently give a faster, more frantic expansion rate than the prediction from the early universe. The gap is not large, but it is stubborn, persisting even as both sets of measurements become more and more precise. This is not a minor quibble. It is a direct challenge to the standard model of cosmology, the very framework we use to understand the universe's history and composition. If this tension is real and not some hidden error in our measurements, it means our model is incomplete. We might be missing an ingredient. Perhaps dark energy is not a constant but is evolving, growing stronger over time. Or maybe a new, unknown type of subatomic particle was flooding the early cosmos, subtly altering its evolution. Another, more radical possibility is that dark matter itself possesses weird, unexpected properties. The Hubble tension is a cosmic alarm bell, a signal that the comfortable story we have been telling about the universe might need a dramatic rewrite. Every new observation sharpens this dilemma, forcing us to confront a simple, unsettling truth. Either we are making a collective mistake we cannot yet see, or the universe is quietly operating by rules we have yet to discover. A single, powerful signal once pierced the cosmic static, a burst so perfect it compelled its discoverer to scrawl one word on the data printout: wow. On August 15, 1977, the Big Ear radio telescope at Ohio State University recorded a 72-second narrowband radio signal that was, for one brief moment, everything we hoped to find. It was strong, it was focused, it appeared to originate from a region in the constellation Sagittarius with no known stars. Most importantly, it matched the precise frequency and profile scientists predicted for an artificial interstellar broadcast. It was the signal that should not have been there, a perfect candidate for a message from another world. And then it was gone. Despite decades of relentless searching by astronomers around the globe, the WOW signal never repeated. It was a one-time event, a cosmic shout into the void that we happened to be listening at the exact right place for the exact 72 seconds to hear. The silence that followed is as much a part of the mystery as the signal itself. What could possibly explain such a perfect, fleeting event? In 2016, a controversial explanation emerged, suggesting the signal might have been a reflection from a passing comet. The theory proposed that the hydrogen clouds surrounding comets could have bounced a human-made transmission back to Earth, creating a temporary, brilliant echo. This idea, however, has been widely criticized and largely dismissed by the scientific community. The comets in question were not even in the telescope's field of view at the time, and the specific frequency of the signal makes such a reflection highly improbable. With a comet explanation failing to convince, we are left with the original, breathtaking possibilities. It could have been a one-time burst from a powerful, natural astrophysical phenomenon we do not yet understand. Or it could have been exactly what it seemed, a transient message from an intelligent civilization. Perhaps it was a targeted beacon sweeping across the galaxy like a lighthouse beam, and Earth just happened to be in its path for a single glorious pass. Maybe it was the equivalent of a cosmic SOS, a final, desperate broadcast from a dying world. Or consider a more humbling thought. What if it was an accidental transmission, the equivalent of a civilization's early radio or television broadcasts leaking into space, a ghost of a signal that traveled for centuries only to fade before anyone could answer? The WOW signal endures not as an answer but as the ultimate question. It is a tantalizing data point of one, a reminder that the universe is capable of producing wonders that defy easy explanation. It fuels the hope that somewhere in the vast silence, someone or something might also be listening. The profound silence of the cosmos is occasionally broken by a scream. In the span of a single blink, a flash of radio energy can release more power than our sun emits in 80 years. These are fast radio bursts, or FRB, intense and mysterious signals that appear randomly from the depths of interstellar space. For years after their initial discovery, these bursts were solitary events, one-off explosions that vanished as quickly as they appeared, leaving astronomers with virtually nothing to study. They were cosmic ghosts, impossible to predict and even harder to understand. The mystery deepened when astronomers found something they never expected, a fast radio burst that repeated. Unlike its one-time cousins, this signal flashed again and again from the same patch of sky, proving that whatever was causing these explosions was not always destroyed in the process. This was a monumental clue, transforming FRBs from frustrating phantoms into tangible objects that could be watched and studied. So what cosmic engine can produce such staggering energy in a mere millisecond? The leading suspect is a type of stellar corpse called a magnetar. Imagine a neutron star, the incredibly dense remnant of a supernova explosion, but with a magnetic field so powerful it could erase a credit card from halfway to the moon. These magnetars can experience starquakes, violent ruptures on their crystalline surfaces that release titanic shudders of energy. Or they could be caused by magnetic flares, explosions in the star's magnetosphere that are trillions of times more powerful than any solar flare. The physics fits, and we have detected an FRB from within our own galaxy that was linked to a known magnetar, providing the first solid piece of the puzzle. Yet, the sheer diversity of FRBs suggests we might be dealing with more than one culprit. Some bursts seem to come from environments dense with hot plasma, like the regions near supermassive black holes. Others have been traced to distant, merging galaxies, hinting that colossal cosmic collisions might be capable of generating these fleeting flashes. This has led to more speculative and thrilling possibilities. Could some FRBs be the result of cosmic strings, theoretical defects in the fabric of spacetime snapping like a gigantic rubber band? Or, as some have dared to propose, could they be evidence of advanced technology? A civilization might use incredibly powerful bursts of energy to propel light sails across interstellar distances, and we would see these beams as brief, brilliant flashes as they sweep past our telescopes. While the extraterrestrial hypothesis remains a long shot, its very consideration highlights how truly enigmatic these signals are. Each new detection is a piece of a cosmic jigsaw puzzle, revealing a universe far more dynamic and violent than we ever imagined, where the quiet hum of empty space is punctuated by sudden, inexplicable shouts. Far beyond the orbit of Neptune, our solar system does not simply fade into the dark. It is fringed by the Kuiper Belt, a vast donut of icy worlds left over from the planet-building era. But this distant realm holds a strange and abrupt boundary, a place where the cosmic census plummets. Astronomers call it the Kuiper Belt Cliff. For decades, our telescopes have been cataloging these frozen relics, and a clear pattern has emerged. Up to a distance of about 50 astronomical units from the Sun, 1 AU being the distance from Earth to the Sun, we find a rich population of objects. Then, beyond that line, the number of detected bodies falls off a cliff. It is not a gentle tapering off, but a dramatic and puzzling drop. It is as if the solar system's construction crew just stopped working at a specific survey line, leaving the outer lot mostly empty. This is not what we would expect from a natural, smoothly distributed disk of debris. So what carved this sharp edge into the frozen fringe of our cosmic neighborhood? One compelling theory points to the gravitational hand of an unseen architect. The sudden emptiness could be the signature of a hidden planet, a world several times more massive than Earth, orbiting in the profound darkness far beyond the cliff. This hypothetical planet 9, whose existence is inferred from the clustered orbits of other distant objects, could be acting as a gravitational shepherd. Its immense pull over billions of years would have either flung most of the icy bodies in that region into the deep darkness of interstellar space, or swept them up into its own orbit, effectively clearing out a vast swath of the Kuiper belt. The cliff would be the fence line of its gravitational domain, yet not all scientists are convinced we need a new planet to solve this mystery. An alternative explanation looks back in time to the very birth of the solar system. Our sun was born in a stellar nursery surrounded by a protoplanetary disk of gas and dust. It is possible that this disk itself had a sharp outer edge, perhaps sheared off by the gravitational tug of a passing sibling star in that crowded early cluster. If the raw material for planet formation simply ran out at that specific distance, then the Kuiper belt cliff is not a cliff at all, but the original shoreline of the solar system's primordial ocean. The emptiness beyond is just that, empty, because there was never much there to begin with. Each theory paints a dramatically different picture of our cosmic home. Is our solar system dynamically alive, still shaped by the unseen movements of a giant ghost planet? Or is the Kuiper belt cliff a frozen fossil, a permanent scar from a traumatic stellar childhood? The answer lies in counting more of these faint, distant objects, a painstaking task that will ultimately tell us whether we are waiting to discover a new world or simply reading the last page of our solar system's construction plans. Deep within the heart of a neutron star, matter is crushed into a state so extreme it defies imagination. Here, the distinction between atomic nuclei and free neutrons blurs into a continuous, dense sea. It is in this alien environment that one of nuclear physics' most controversial ideas might find a home, the tetraneutron. This is a hypothetical particle, a stable cluster composed of 4 neutrons and nothing else. Its very existence would shatter a fundamental rule of our current models. The nuclear force that binds protons and neutrons is often described as a kind of glue, but it is a glue with very specific requirements. It works best in a mix, holding protons and neutrons together in a tight embrace. According to every established theory, a cluster of only neutrons should not be able to bind itself together. The attractive force between 2 neutrons is simply too weak to overcome the inherent instability. It would fly apart in an instant. A tetraneutron should be impossible. Yet experiments have repeatedly hinted that it might be real. The story begins with particle collisions. Researchers smash stable atomic nuclei into thin targets, and in the debris of these miniature explosions, they look for signatures of the impossible. Some experiments have detected a signal, a resonant state that looks exactly like a tetraneutron appearing for a fleeting moment before it disintegrates. The data suggests this 4-neutron system holds together for just a billionth of a second. That may seem impossibly short, but in the quantum world, it is long enough to be significant. It is long enough to suggest that our understanding of the nuclear force is incomplete. These findings are fiercely debated. Other research teams performing similar experiments with different setups have found nothing but empty space where the tetraneutron signal should be. The scientific community is divided, caught between tantalizing evidence and rigorous skepticism. The central question is whether these experiments are truly creating a bound tetraneutron, or if they are merely observing a temporary, unbound quartet of neutrons that just happen to be flying in close formation for a brief moment before they scatter. If the tetraneutron is confirmed, the implications would ripple across physics. It would force a rewrite of the textbooks on the strong nuclear force. We would have to accept that this fundamental force can act in a way we never predicted, creating bonds where none should exist. This new understanding would instantly shed light on the most mysterious objects in the cosmos, neutron stars. The cores of these stellar corpses are a soup of neutrons under unimaginable pressure. If a tetraneutron can be stable in a laboratory for even a sliver of a second, could similar, even larger clusters of pure neutrons form in the intense density of a neutron star? The interior of these stars might not be a uniform fluid, but a strange landscape of exotic, neutron-rich islands. The tetraneutron is more than a particle hunt. It is a direct test of our models at the very edge of stability, a probe into the forces that shape not just atoms, but the universe's most compact objects. Its confirmation or refutation will ultimately tell us if the glue that holds reality together is exactly as we think, or if it has a secret, hidden strength we are only beginning to glimpse. The search for cosmic anomalies leads us from the fleeting existence of subatomic particles to a permanent scar on the sky, a place where the universe's ancient light is strangely cold. Known as the CMB cold spot, this region in the cosmic microwave background is far larger and far colder than our best models can easily explain. It is a colossal bruise on the infant universe, a patch of sky where the temperature drops just a few millionths of a degree below the average. While that sounds minuscule, its size is staggering, spanning 1 billion light-years across. This is not a tiny statistical blip. It is a cosmic continent of cold in a sea of uniformity, and its existence challenges our understanding of how the cosmos evolved. One leading theory suggests we are looking at a ghost. This could be a supervoid, an unimaginably vast and nearly empty region of space that our galaxy is beginning to traverse. As light from the cosmic microwave background travels through such a void, it must climb out of a gravitational well. In an expanding universe dominated by dark energy, this climb saps the light's energy, stretching its wavelengths and making it appear colder to our telescopes. It is a process called the integrated Sachs-Wolf effect. The cold spot in this view is a shadow cast by the greatest nothingness we have ever encountered, a 1 billion light-year-wide hole in the cosmic structure. Yet, even this dramatic explanation has its problems. Surveys mapping the distribution of galaxies have indeed found evidence of a large underdense region in the direction of the cold spot, but the void does not seem quite large enough or empty enough to account for the profound cold we observe. The numbers do not fully add up, leaving a gap in our understanding. This discrepancy fuels a far more spectacular possibility. Could the cold spot be evidence of a cosmic collision? Some cosmologists propose it is a remnant of our universe's violent birth during the period of inflation, a time when space itself expanded faster than light. In this theory, our nascent universe might have bumped into another bubble universe in the wider multiverse. The energy released in such a collision would have left a permanent, cooler imprint on our cosmic background radiation, a cosmic birthmark from a long-ago encounter with a reality we can never directly see. This idea pushes the boundaries of physics, suggesting that the cold spot is not a feature of our universe alone, but a fingerprint from a neighboring one. So, are we witnessing the shadow of a colossal emptiness or the echo of a multiversal crash? The debate is a classic scientific standoff between the mundane and the magnificent. Is the cold spot a rare but natural cosmic structure, a statistical outlier in an otherwise predictable cosmos? Or is it a crack in the cosmological principle, a sign that our universe is not as isotropic as we believed, forever marked by an event from beyond our own spacetime? Each new observation of this frigid expanse brings us closer to an answer, one that will either constrain the universe to a set of known rules or fling open a door to realities beyond our own. This relentless expansion of space forces us to confront a more intimate mystery, the nature of time itself. We feel its flow as an undeniable current, carrying us from a fixed past into an uncertain future. Yet physics insists that the fundamental laws, from gravity to quantum mechanics, are completely symmetric. They work just as well if time runs forward or backward. So why does our experience of time have such a definite, one-way arrow? The answer appears to be written in the language of disorder. Entropy, a measure of randomness or chaos in a system, is the only physical quantity that provides a clear direction for time. Think of an ice cube melting in a glass of warm water. The highly ordered, low-entropy state of the solid ice always evolves into the disordered, high-entropy state of liquid water, perfectly mixed. You never see the reverse happen spontaneously in nature. The water in your glass does not suddenly reorganize itself into an ice cube while heating the room around it. The universe as a whole began in an incredibly ordered, low-entropy state at the Big Bang, and it has been sliding toward a state of maximum entropy or heat death ever since. Our perception of time's flow is us witnessing this cosmic progression from order to disorder, but this leads to a profound debate. Is time a fundamental property of the universe, a basic ingredient woven into its fabric, or is it merely an emergent phenomenon, an illusion that arises from the collective behavior of countless particles increasing their entropy? Some physicists propose a radical idea called the block universe. In this view, all of time, the past, present, and future, exist simultaneously in a single, static four-dimensional structure. Your birth, your life, and your eventual death are all equally real, fixed points in this cosmic block. The feeling of a flowing now is just a quirk of our consciousness, a mental bookmark moving through the eternal pages of a book that is already completely written. This challenges our deepest intuitions about free will and reality. Are we truly making choices, or are we just following a path that has always been there? The mystery of time forces us to ask what we really are. Are we active participants in a dynamic universe, or are we simply eternal patterns in a frozen block of space-time, momentarily aware of the page we are on? This fundamental bias is etched into every living cell on our planet. Amino acids, the building blocks of proteins, come in two mirror image forms, left-handed and right-handed, much like a pair of human hands. In the chemical soup of early Earth, you would expect both versions to form in equal amounts. Yet every organism, from the simplest bacterium to the largest whale, uses exclusively left-handed amino acids to construct its proteins. The same strange rule applies to sugars, the backbone of DNA and RNA, which in all known life are exclusively right-handed. This universal preference is called homochirality, and it is a mystery that strikes at the very origin of life itself. Why would nature choose one hand over the other? If life started from a random chemical process, we should see a mix, a racemic soup of both left and right-handed molecules. The fact that we do not suggests that some influential bias tipped the scales at the very dawn of biology. One compelling theory looks to the stars for an answer. In the cold, dark clouds of interstellar space, complex organic molecules form on the surfaces of dust grains. These molecular nurseries are not completely neutral. They are bathed in the faint light of distant stars, and some of that light is circularly polarized. This means the light waves spiral through space, either clockwise or counterclockwise, and this spin can selectively break down one form of a chiral molecule over the other. A particularly powerful source of this polarized light could be neutron stars, whose intense magnetic fields can polarize the radiation they emit across vast distances. If our solar system formed in a cloud that had been irradiated by such a source, the initial organic compounds delivered to early Earth by comets and meteorites might have already carried a slight excess of left-handed amino acids. This tiny initial bias, amplified over millions of years of chemical evolution, could have set the template for all life to follow. Another, even more profound possibility is that this homochirality is not a local fluke but a universal law. Perhaps the weak nuclear force, one of the four fundamental forces of nature, is inherently chiral. its influence on certain radioactive decay processes very subtly favors left-handedness over right-handedness. This fundamental asymmetry, woven into the fabric of reality, could have imprinted itself on the first complex molecules, making left-handed amino acids the statistically inevitable choice anywhere in the cosmos where life emerges. The final theory is perhaps the most speculative, suggesting that life did not actually begin on Earth at all. The panspermia hypothesis proposes that the basic ingredients for life, or even primitive life itself, hitchhiked across space on asteroids or comets. In this scenario, the homochirality of life was already established on another world, and we are simply the recipients of that cosmic legacy. Our entire biosphere would then be a clone, a descendant of a single genesis event that occurred somewhere else in the galaxy. Each of these ideas carries a different implication for our place in the universe. Is our left-handed life a rare accident, a product of a specific stellar environment? Is it the universal standard, a signature of physics itself? Or is it a fossil, a clue pointing to our true cosmic ancestry? The answer, locked within the very molecules that build our bodies, would tell us if the chemistry of life is a random roll of the dice or a fixed rule written in the stars. This single number, the vacuum energy, is a ghost haunting the heart of theoretical physics. It represents the energy density of empty space itself, the faint hum of quantum fields that, according to our best theories, should be buzzing with incredible activity. In the framework of quantum field theory, empty space is not truly empty. It is a seething sea of virtual particles that constantly pop in and out of existence, each pair contributing a tiny bit of energy to the vacuum. When physicists attempt to calculate the sum total of all this activity, the result is a number of such staggering magnitude it defies comprehension. The theoretical prediction for the vacuum energy density is a value of 10 to the power of 112 in those units. That is a 1 followed by 112 zeros. This is arguably the worst prediction in the entire history of science. Yet, when we look out at the cosmos and measure the actual strength of the force driving the universe's accelerated expansion, the observed value for this vacuum energy is almost zero. To be precise, it is a value of around 10 to the power of -8 in the same units. The discrepancy between the colossal prediction and the tiny observation is a factor of 1 followed by 120 zeros. This is not a small error that can be brushed aside. It is a chasm so vast it suggests something is fundamentally wrong with our understanding of reality. The challenge this poses is profound, for it strikes at the very core of our two most successful physical theories. On one hand, we have quantum field theory, which describes the world of the very small with breathtaking accuracy. On the other, we have Einstein's general relativity, which masterfully describes the cosmos and gravity. Both are monumental achievements, yet they are seemingly incompatible on this one crucial point. The vacuum catastrophe suggests that when we try to merge these two frameworks, our mathematics produces a result that is catastrophically, unimaginably wrong. How can the predicted energy of nothing be so enormous, while the measured energy of the cosmos is so infinitesimally small? One desperate solution is the concept of a multiverse. In this view, our universe is just one bubble in a vast cosmic foam, each with its own random value for the vacuum energy. We simply happen to live in one of the rare bubbles where this number is small enough to allow galaxies, stars, and life to form. In most other universes, the vacuum energy is so large it either tears space apart instantly or causes it to collapse back on itself, making life impossible. This is an elegant but unsettling answer, as it makes our existence a matter of pure, random chance rather than a necessary outcome of fundamental laws. The vacuum catastrophe is more than a mathematical embarrassment. It is a direct challenge, a glaring signpost that we are missing a deep piece of the puzzle. It forces us to ask whether our theories of the quantum and the cosmic are fundamentally incomplete, waiting for a new Einstein to show us how to reconcile the energy of nothing with the everything we see. A fossilized rain of stone buried in the rock of our planet tells a story of cosmic chaos and biological rebirth. Around 466 million years ago, during the Ordovician period, Earth was bombarded by a prolonged meteor shower that lasted for millions of years. The evidence is not in a single massive crater, but in a fine dust of extraterrestrial material scattered across ancient seafloors worldwide. Geologists find this record in the form of tiny, glassy spherules and an unusual concentration of the element iridium, a metal rare on Earth's surface but common in asteroids. This was not a single catastrophic impact like the one that doomed the dinosaurs. It was a slow, steady drizzle of cosmic debris that fundamentally altered our world. The timing of this celestial storm is what makes it so extraordinary. It did not trigger a mass extinction. Instead, it coincided with the Great Ordovician biodiversification event, a dramatic explosion in the variety and complexity of marine life. For a long time, life in the oceans had been relatively simple. Then, as the meteors fell, the fossil record shows a sudden and spectacular proliferation of new species, from intricate corals and powerful, shell-crushing predators to the first primitive relatives of starfish and sea urchins. How could a bombardment from space possibly create such a fertile environment for life? The answer may lie in a gradual, global cooling. The constant influx of fine dust high in the atmosphere would have acted as a planetary sunshade, reflecting a fraction of sunlight back into space. This gentle, long-term cooling broke up the previously stable and warm global climate, creating a patchwork of new environments and temperature zones in the oceans. Life, forced to adapt or perish, did what it always does when faced with new challenges. It diversified, innovated, and exploded into a multitude of new forms to fill every newly created niche. This presents a cosmic paradox. The same process that can deliver a single, civilization-ending asteroid can also deliver a slow, life-giving rain. The key is the dosage and the duration. A sudden, violent impact is a trauma. A prolonged, gentle shower is a form of climate engineering orchestrated by the solar system itself. But what caused this million-year meteor shower? The leading theory points to a colossal collision far out in the asteroid belt between Mars and Jupiter. A massive asteroid likely shattered in a cosmic crash, scattering a cloud of fragments throughout the inner solar system. For millions of years, Earth's orbit swept through this debris field, collecting the shattered remains of that primordial accident. This idea transforms our understanding of our place in the cosmos. We are not just isolated on a pale blue dot. The history of our biosphere is inextricably linked to the gravitational dynamics and violent accidents occurring in the asteroid belt. A collision 500 million kilometers away can, over eons, determine the fate of life on our world, not with a bang, but with a whisper of dust that coaxes evolution into a faster, more vibrant dance. It forces us to wonder whether the vibrant tapestry of life we see today owes its very existence to a forgotten cataclysm among the asteroids. The ancient rain of meteors that shaped our world was a local event, but in 2017, our solar system received a visitor from a truly foreign shore. The Pan-STARRS telescope in Hawaii spotted a faint point of light moving at incredible speed, an object so unusual it was named Oumuamua, Hawaiian for scout. It was the first interstellar object ever detected passing through our cosmic neighborhood. Its trajectory was hyperbolic, meaning it was not bound by the sun's gravity, a rock from another star simply cutting through our system. But its true oddness became clear as astronomers tracked its path. Its brightness varied wildly as it tumbled, suggesting an extreme, elongated shape, perhaps 10 times longer than it was wide, like a cosmic cigar or a pancake tumbling through the void. Nothing in our solar system looks quite like it. Then came the real puzzle, its acceleration. As Oumuamua sped away from the sun, its velocity changed in a way that could not be explained by gravity alone. Something was giving it an extra push. For a normal comet, this is a solved case. The sun's heat vaporizes ices on its surface, and the jet of released gas acts like a tiny thruster, a process called outgassing. The problem was, Oumuamua showed no visible coma, the classic cloud of gas and dust that surrounds a comet's nucleus. Our telescope saw no outgassing, no tail, no debris. It was a rock seemingly pushing itself without any visible exhaust. This non-gravitational acceleration forced scientists to consider extraordinary possibilities. The mainstream explanation holds that it was still a comet, just a very peculiar one. Perhaps it was made of very pure hydrogen or nitrogen ice. When such ices sublimate, they produce a gas that is transparent to our telescopes, a stealthy jet that would push the object without leaving a visible trace. Or maybe it was a fractal-like aggregate of dust, a cosmic dust bunny so porous and lightweight that the gentle pressure of sunlight itself could have provided the observed nudge. But the absence of clear, conventional evidence opened the door for a more breathtaking hypothesis. Harvard astronomer Avi Loeb famously proposed that Oumuamua could be a piece of advanced alien technology. Its unusual shape and its mysterious acceleration, he argued, were consistent with a light sail, a vast, thin structure designed to catch the radiation pressure from stars for propulsion. A broken fragment from a larger vessel tumbling through the galaxy as space junk would exhibit exactly the kind of behavior we witnessed. It would be thin and light, explaining the shape. It would gain a push from solar radiation pressure, explaining the acceleration without any need for outgassing. The idea ignited a fierce debate that continues to this day. Is Oumuamua a testament to the bizarre but natural diversity of objects forming around other stars, a type of world we had simply never imagined? Or was it our first brush with an artifact, a message in a bottle that sailed right past us before we even knew how to read it? The object is now long gone, racing back into the interstellar dark, taking its secrets with it. Its brief visit serves as a permanent reminder that the universe is capable of crafting wonders that defy our easy categories, forcing us to look up and wonder what else might be passing silently in the night. The same quantum strangeness that governs the smallest particles might also hold the key to the cosmos itself. At the heart of this lies the quantum measurement problem, a puzzle so deep it questions the nature of reality. In the quantum realm, particles do not have definite properties until we measure them. An electron, for instance, exists in a blur of all possible positions and spins at once, a state called superposition. It is only when we observe it that this cloud of possibilities collapses into a single, concrete fact. But what exactly counts as a measurement, and who or what gets to do the collapsing? This is not just a technicality. It is a gaping hole in our understanding of how the universe operates. The most traditional answer is the Copenhagen interpretation. It simply states that the act of observation by a conscious observer causes the wave function to collapse. In this view, reality is fundamentally probabilistic until a conscious mind looks at it, making our awareness a bizarrely central player in the cosmos. Yet this raises a haunting question. Was the moon not there before the first creature looked at it? This interpretation places human consciousness on a pedestal that many physicists find deeply uncomfortable. A far more radical solution is the many worlds interpretation. It proposes that the wave function never collapses at all. Instead, every time a quantum event has multiple possible outcomes, the entire universe splits into branches. In one universe, the electron spins up. In another, perfectly real universe, it spins down. Every choice, every random quantum event spawns new parallel realities. In this view, there is a universe where you never started watching this video, and another where you are already an expert on dark energy. The cosmos becomes a forever branching tree of every possibility, a multiverse in the truest sense. This interpretation removes the special role of the observer. but at the incredible cost of an infinitely proliferating reality. A third, more recent idea suggests that the answer is written in the fabric of space and time. The process of wave function collapse might not need a conscious observer, but could be triggered by gravity. In this scenario, when a quantum system becomes too large or massive, its own gravitational pull forces it to choose a single classical state. The universe itself, through gravity, is the ultimate observer, constantly collapsing probabilities into facts. This would weave quantum mechanics and general relativity together in a way we have never seen, making the cosmos an active participant in defining its own reality. The quantum measurement problem forces us to confront the very meaning of existence. Is reality created by our gaze? Does every decision we make spawn an infinite number of shadow selves in unseen worlds? Or is the universe simply too heavy to remain in a state of maybe? We are left staring into the quantum abyss, wondering if the act of looking up at the stars is, in some small way, what makes them real. Every magnet you have ever held, from a simple fridge decoration to the one inside a compass, is a cosmic diplomat. It tirelessly demonstrates a fundamental rule of our universe. Magnets always come with two poles, a north and a south. Snip a standard bar magnet in half, and you do not get isolated poles. You simply get two new, smaller magnets, each with its own inseparable north and south. This duality seems as fixed as the laws of physics themselves. Yet, our most ambitious theories of the cosmos insist that this was not always the case. In the searing heat of the Big Bang's first moments, the fundamental forces of nature were unified into a single, supreme interaction. As the universe cooled and expanded, this symmetry broke, and the forces we know today, gravity, the strong and weak nuclear forces, and electromagnetism, froze out into their distinct identities. This grand theoretical framework, known as a grand unified theory, makes a startling prediction. The process of this symmetry breaking should have created staggering numbers of a hypothetical particle, the magnetic monopole. A monopole is exactly what it sounds like, a particle that is a pure north magnetic pole, or a pure south, existing completely on its own. It would be the magnetic equivalent of an isolated electric charge, like finding an electron that was only negative without a corresponding positive proton. According to the math, these cosmic relics should be everywhere, so massive and stable that they would have survived from the earliest instant of time. They should be as common as protons, meaning there should be at least one in every liter of space in the solar system. Our planet should be littered with them. But we have never found a single one. This is the monopole problem. Where did they all go? The leading solution is one of the most mind-bending concepts in all of cosmology: cosmic inflation. This theory proposes that a fraction of a second after the Big Bang, the universe underwent a brief, exponential growth spurt, inflating from smaller than a proton to a colossal size in an unimaginably short time. This inflationary period did not just make the universe vast, it also made it incredibly smooth and uniform, ironing out wrinkles that would become the seeds for galaxies. Crucially, it would have diluted the density of any primordial monopoles to virtually zero. Imagine you had a single grain of sand and then suddenly expanded the entire Sahara Desert to the size of the observable universe. The chance of ever finding that one specific grain again becomes infinitesimally small. Cosmic inflation did exactly that to magnetic monopoles. It scattered them so thinly across the cosmos that finding one in our observable patch of universe becomes a monumental task. This makes the ongoing search for a monopole a high-stakes cosmic treasure hunt. Physicists have set up incredibly sensitive experiments using loops of superconducting wire that can detect the tiny magnetic shift a passing monopole would cause. They have examined moon rocks and deep-sea sediments, searching for the unique scars a heavy, charged monopole would leave as it passed through matter. So far, every search has come up empty. This enduring silence is a powerful clue. It strongly supports the theory of inflation, yet it also deepens the mystery. Is our universe truly so vast that all the monopoles are simply out of reach, lost in the cosmic deep? Or could our understanding of grand unification be subtly wrong, pointing toward a different kind of physics at the highest energies? The quest for a single, lonely North Pole without its south is more than a particle hunt. It is a direct test of our universe's most violent and formative moment, a search for a ghost that should be everywhere, yet remains the one magnet we cannot find. This perfect flatness of our universe is a clue of its own, a whisper from the beginning that something had to force it into such a precise shape. The geometry of the cosmos is not a given. According to Einstein's theory of gravity, space itself can be curved by the matter and energy within it. This curvature can take one of three forms. The universe could be closed like the surface of a giant sphere, eventually curving back on itself. It could be open, shaped like an infinite saddle, curving away forever. Or, against all odds, it could be perfectly flat, like an endless sheet of paper where parallel lines never meet and never diverge. For the universe to be flat, the density of all the mass and energy it contains must be exactly at a specific critical value. This is a knife-edge balance. If the density were even the tiniest bit higher in the first second after the Big Bang, the universe would have quickly collapsed back in a big crunch. If it were the slightest bit lower, it would have expanded so rapidly that galaxies and stars could never have formed. The universe would be a cold, empty void. Our measurements tell us that the actual density is astonishingly close to this critical value. The fine-tuning required is beyond extreme. To achieve the flatness we see today, the initial density at 1 second after the Big Bang had to be fine-tuned to within 1 part in 10 to the power of 60. That is a 1 followed by 60 zeros. It is like balancing a pencil on its tip for billions of years, a feat of such improbable precision that it seems to demand an explanation beyond pure chance. How did the universe get so perfectly balanced? The most powerful answer, once again, is cosmic inflation. This theory proposes that a tiny, random patch of the primordial universe was sent into a phase of hyper-fast expansion, inflating by a factor of trillions upon trillions in a fraction of a second. Think of the surface of a crinkled, wrinkled balloon. If you inflate that balloon to an immense size, any small section of its surface will appear perfectly flat to a tiny ant crawling on it. Inflation did exactly that to the fabric of space-time. It took whatever curvature the infant universe had and stretched it out on such a colossal scale that from our limited perspective within it, the cosmos appears perfectly flat. The flatness is not a mysterious initial condition. It is a consequence, a predictable outcome of the universe having been blown up to such an enormous size. This solves the fine-tuning problem not by invoking chance, but by showing how a wild, explosive growth spurt ironed out the wrinkles and forced the cosmos into the geometric straitjacket we observe. The universe is flat because inflation made it so vast that we can no longer perceive its curvature, forever living on a seemingly infinite plane born from an unimaginable stretch. The entire cosmos glows with the same warmth. From every direction we look, the faint afterglow of the Big Bang, the cosmic microwave background, shows a nearly identical temperature down to a few 10,000ths of a degree. This uniformity is deeply puzzling, a cosmic coincidence that should be impossible. Think of 2 cups of coffee placed on opposite sides of a vast, cold room. Left to themselves, they would never reach the same temperature unless something mixed them together. The universe presents us with exactly this scenario. Regions of space on opposite sides of the observable sky have been flying apart since the beginning, and according to the standard Big Bang model, they have never been close enough for heat to flow between them. They were never in causal contact, so how did they manage to coordinate their temperature so perfectly? This is the horizon problem, and it suggests that the early universe was far more intimately connected than its initial conditions allow. The most compelling solution is once again a period of breathtaking violence, cosmic inflation. This theory rewinds the tape to a tiny fraction of a second after creation. Before inflation, the entire observable universe was crammed into a volume trillions of times smaller than an atom. In this incredibly hot, dense state, every particle was in direct contact with every other, allowing energy to be evenly distributed, achieving a perfect, uniform temperature. Then inflation struck. A field of energy inherent to space itself triggered a phase of hyper-fast expansion, blowing that tiny, connected patch up to a size larger than our entire observable universe in less time than it takes light to cross a proton. This explosive growth stretched that initial uniformity across the entire sky, locking in the same temperature everywhere. The regions that now appear on opposite horizons were once neighbors, close enough to share a cosmic handshake before being flung apart by the inflationary wind. Without this mechanism, the smooth, uniform cosmos we see would be an inexplicable miracle. With it, the horizon problem transforms from a paradox into a prediction, a fossilized echo of the universe's most dramatic growth spurt. Our universe should not exist. The Big Bang, in its raw, explosive birth, should have created equal amounts of matter and antimatter. For every proton born, an antiproton should have emerged. For every electron, a positron. These are perfect opposites, identical in mass but with opposite electrical charge. Whenever a particle meets its antiparticle, they annihilate in a flash of pure energy, leaving nothing behind. So if the cosmos began with a perfectly balanced ledger, all of its constituent parts should have mutually destructed in a brilliant, all-consuming flash, leaving behind a sea of radiation and nothing more. No stars, no planets know us, yet here we are. Every galaxy, every star, and every living thing is testament to a single profound fact. Somehow, for every billion pairs of matter and antimatter that annihilated in the early universe, one single particle of matter was left over. That 1 in a billion surplus is everything we see and know. This is the Barrian asymmetry problem, and it is the ultimate question of why there is something instead of nothing. To solve this, physicists have outlined 3 key conditions that must have been met in the universe's first moments, a cosmic recipe for creating matter. First, there had to be a process that treated matter and antimatter differently, violating a fundamental symmetry known as charge parity, or CP. Second, the universe had to be out of thermal equilibrium, meaning it was not a smooth, uniform soup, but had the necessary turbulence for the imbalance to take root. And third, these processes had to violate Barrian number, a law that says the total amount of matter in the universe should be conserved. We have actually found a piece of this puzzle. In the 1960s, scientists discovered CP violation in the decay of certain exotic particles called kaons. This proved that nature does, on a very small scale, have a tiny preference for matter over antimatter. The problem is, the amount of CP violation we have observed is far too weak to account for the overwhelming dominance of matter we see in the cosmos. It is like finding a single drop of water and trying to explain the existence of all the oceans. So the hunt is on for new, more powerful sources of this symmetry breaking. Experiments like the Large Hadron Collider are smashing particles together at incredible energies, recreating the conditions of the early universe to see if new, undiscovered particles might carry a stronger matter bias. Meanwhile, incredibly precise studies of the properties of neutrons and other subatomic particles are searching for any tiny deviation from perfect symmetry, any whisper of a preference that could have tipped the cosmic scales. The answer might lie in the ghostly neutrino. If these elusive particles are their own antiparticles, a property known as Majorana fermions, they could have triggered a process called leptogenesis in the infant cosmos. This would have created an imbalance in leptons, which then transformed into the Barrian imbalance we see today. Every breath you take is filled with the legacy of that primordial victory. The air, the ground, your own body are all made from that 1 in a billion relic, the survivors of the universe's first and most decisive war. Our galaxy is not simply drifting through the void. It is being pulled, along with thousands of its neighbors, toward a specific point in the cosmic darkness. This mysterious focal point of gravity is known as the Great Attractor, a colossal anomaly located some 250 million light-years away in the direction of the Centaurus constellation. The sheer force required to tug on entire galaxies hints at a concentration of mass almost incomprehensibly large, a gravitational sink in intergalactic space that commands the motion of our entire local supercluster. Yet for decades, this cosmic magnet remained one of the most frustrating puzzles to study, because it lies directly behind the plane of our own Milky Way. This region is called the Zone of Avoidance, a dusty, star-choked lane that obscures nearly 20% of the wider universe from our view. It is like trying to see a distant mountain range through a perpetual, blinding sandstorm. Our own galactic backyard is blocking the view of the most significant gravitational force we are falling toward. Early observations could only sense its pull, like feeling a powerful wind without being able to see what was causing it. What could possibly be massive enough to exert such a force? The initial theory pointed to a known, but still immense, structure called the Norma Cluster, a dense gathering of galaxies that sits at the heart of this gravitational anomaly. But further measurements revealed a startling truth. The pull was too strong, the velocity of our galactic motion too great. The mass of the Norma Cluster alone was insufficient to account for the relentless tug. The Great Attractor was not a single cluster, but merely the foreground of something far grander. This realization shifted our cosmic perspective entirely. We now understand that the Great Attractor is just a local part of an even more immense structure, the Laniakea supercluster. Laniakea, which means immense heaven in Hawaiian, is a cosmic filament of 100,000 galaxies, all flowing along gravitational watersheds toward the same vast basin. Our Milky Way, the Andromeda Galaxy, and the entire Virgo supercluster are but minor suburbs in this sprawling galactic metropolis. The Great Attractor is not the final destination, but a major waypoint in a much longer cosmic journey. So what lies at the true center of this pull? The leading hypothesis suggests an overwhelming concentration of dark matter, the invisible scaffolding of the cosmos, weaving thousands of galaxies into a single, gravity-bound network. It is the shadowy hand of dark matter, sculpting the largest rivers of motion in the universe. Our galaxy's path is not a random drift, but a single thread in a tapestry of gravity woven on a scale so vast we are only just beginning to trace its patterns. Deep within the heart of our own galaxy, an invisible beacon is screaming in pure light. The center of the Milky Way blazes with an unexpected and powerful excess of gamma-ray radiation, the most energetic form of light in the universe. This is not the gentle glow of starlight, but a fierce, unexplained shout. When scientists meticulously mapped this high-energy light, they found a spherical halo of gamma rays radiating from the galactic core, a signal that stubbornly refuses to fade into the background. It is a cosmic anomaly, a ghost in the machine of our own celestial backyard, and its origin has become one of the most tantalizing detective stories in modern astrophysics. One compelling explanation points to the shadowy substance that permeates the galaxy. The center of the Milky Way is thought to be densely packed with dark matter, held there by the immense gravity of the central supermassive black hole. If dark matter is made of weakly interacting massive particles, then this is where they would be most concentrated. And if these particles are their own antiparticles, they could annihilate upon collision, converting their mass directly into a flash of gamma rays. The observed excess perfectly matches what many theoretical models predict for such a dark matter signal. It could be the first indirect glimpse of the universe's dominant matter, the ghost finally revealing itself in a burst of self-destruction. Yet the cosmos is rarely so straightforward. A more conventional but no less fascinating explanation involves the stellar dead. The galactic center is a crowded metropolis of ancient stars, and among them are likely thousands of pulsars, the rapidly spinning, lighthouse-like cores of dead suns. These pulsars beam out powerful radiation, including gamma rays. Our telescopes may simply be unable to resolve this vast population of individual point sources, seeing them instead as a single, fuzzy, and uniform glow. This would make the gamma ray excess not a discovery of new physics, but a testament to our technological limitations, a reminder that sometimes a mystery is just a crowd we cannot yet see individually. There is another, more violent possibility buried in the galaxy's past. Our central supermassive black hole, Sagittarius A star, is relatively quiet today. But it may not have always been so. Episodes of intense past activity, when it tore apart and devoured stars or vast clouds of gas, could have accelerated particles to near light speeds, creating outbursts of radiation whose lingering echo we now detect as the gamma ray excess. It would be the fossilized breath of a sleeping dragon, a remnant of a more violent era in our galaxy's history. So, are we witnessing the final, fiery signature of dark matter, or simply the collective hum of a city of dead stars? The debate is a perfect example of scientific caution wrestling with the thrill of discovery. Each new observation sharpens the picture, but the true nature of this galactic heart of light remains one of the most electrifying unsolved puzzles, a secret waiting at the center of our own cosmic home. Even the empty void of space is not what it seems. For an observer hurtling through the cosmos at a constant velocity, space appears as a cold, silent vacuum. But for someone who is accelerating, the story is completely different. According to the predictions of quantum field theory, that same empty space would feel like a warm bath. This is the Unruh effect, a strange and deeply controversial idea suggesting that reality itself depends on your state of motion. An accelerating observer would be surrounded by a faint glow of particles, Unruh radiation, popping into existence in what anyone else would call nothing. The faster you accelerate, the warmer this phantom bath becomes. It is as if motion through nothing can create something from nothing, blurring the line between illusion and substance. This leads to a fierce debate. Is the Unruh effect a real, physical phenomenon, or is it just a mathematical quirk, a trick of how different observers keep their books? The effect is so incredibly faint that for any acceleration we can achieve, the temperature is a billionth of a degree above absolute zero, making it virtually impossible to detect directly. This has left it in a theoretical limbo for decades, yet its implications are profound, especially when we look toward the edge of a black hole. The Unruh effect is a close cousin to Hawking radiation. Just as an accelerating observer sees particles in the void, an observer near a black hole's event horizon would see Hawking radiation streaming out. In both cases, a horizon is key. For the accelerating observer, it is a Rindler horizon, a boundary in space beyond which events can never communicate with them. For the black hole, it is the event horizon itself. Both effects tell us that horizons create particles, transforming the vacuum from a universal constant into a personal experience. This forces a radical question upon us. What is the true nature of empty space? Is there a single objective reality, or does every observer, depending on their path through the cosmos, live in a slightly different universe, each with its own version of the vacuum? The Unruh effect suggests that the particles we use to define reality are not fundamental fixtures of the universe, but emergent properties of our own particular journey through it. The warmth of the void is not out there, but in the eye of the accelerating beholder. The warmth of empty space is a phantom, but the cosmos is flooded with a far more elusive ghost. Billions of these phantoms pass through your thumbnail every single second, a silent rain left over from the Big Bang itself. This is the cosmic neutrino background, a relic sea of the most slippery particles in existence, and its detection stands as one of the greatest technical challenges in all of modern science. Like the cosmic microwave background that gives us a picture of the universe at 380,000 years old, the cosmic neutrino background would be a snapshot from a far more primordial time, just 1 second after creation. To capture, it would be to open a window into the universe's very first breath. The challenge is that these neutrinos have been traveling for almost 14 billion years, and in that time, the expansion of the universe has stretched their wavelengths and sapped their energy to almost nothing. They are now incredibly cold and slow, interacting with matter so rarely that they might as well not be there at all. Detecting them is like trying to hear the faintest whisper in the middle of a hurricane. Every other form of radiation, from starlight to radio waves, drowns out their signal. Every random vibration in a detector, every trace of natural background radioactivity, is a roar compared to the delicate signature of a relic neutrino. So how do you catch a ghost? The most promising ideas are feats of sheer ingenuity. One concept involves building a vast detector filled with a huge mass of a specific isotope like tritium. The idea is to wait for one of these ancient neutrinos to strike a nucleus in just the right way, causing a tiny, specific change that nothing else can mimic. Another proposal is to use a crystal so pure and so cold that the faint kick from a relic neutrino would make it ring like a bell. These experiments would need to be shielded miles underground, protected from cosmic rays, and chilled to a fraction of a degree above absolute zero. It is a hunt conducted in a world of perfect silence and perfect cold, all for a particle that may never show itself. Why go to such extreme lengths? Because the prize is a direct look at the universe before there were atoms, before there was light as we know it. These neutrinos decoupled from the rest of reality when the cosmos was a seething soup of fundamental particles, and they have been flying unchanged ever since. Studying their patterns could reveal secrets about the neutrino itself, like its exact mass, a number we still do not know. It could tell us if there were additional, unknown forces at play in that first second. They are messengers from a time more remote than any telescope can see, carrying a story written in the first chapter of everything. Finding them would mean touching the universe at its moment of birth. There is a wall at the edge of the universe, a theoretical barrier that the most energetic particles should not be able to cross. This is the GZK cutoff, named for the 3 physicists who predicted it. The logic behind it is both simple and profound. The space between galaxies is not a perfect vacuum. It is filled with the faint, leftover glow of the Big Bang, the cosmic microwave background radiation, a sea of ancient photons. When an ultra-high energy cosmic ray, a single proton traveling at almost the speed of light, journeys across billions of light years, it is bound to collide with one of these background photons. For a normal cosmic ray, this is a minor event. But for a proton at the theoretical energy limit, the collision is catastrophic. The impact is so violent it mimics the conditions of the early universe, creating a shower of new particles and sapping the proton's energy. According to our best models, this should place a hard ceiling on the energy of any cosmic ray that travels more than 150 million light-years. No proton from a distant galaxy should reach Earth with an energy beyond this GZK cutoff. The universe, it seems, has a built-in speed limit for its most powerful projectiles. Yet, our detectors have recorded multiple cosmic rays that smash right through this theoretical wall. These are the ultra-high energy cosmic rays that defy explanation. Particles that carry energies millions of times greater than anything we can produce in our largest particle colliders, and they appear to come from vast distances. It is as if a cannonball fired from a distant castle arrived at your doorstep with more force than the cannon itself could possibly have generated. This is the GZK paradox, a direct challenge to our understanding of particle physics and the structure of the cosmos. So how are these cosmic rule breakers getting through? One possibility is that we are wrong about their origins. Perhaps these ultra-high energy particles are not coming from the deep universe at all, but from relatively nearby sources within our own local supercluster of galaxies, a distance short enough to avoid the worst of the GZK barrier. But this only deepens the mystery because we have yet to identify any celestial object in our cosmic backyard with the power to launch such incredible bullets. Another, more thrilling possibility is that the GZK calculation itself is flawed because it relies on the standard model of particle physics. The collisions between cosmic rays and background photons involve energies so extreme that they might be probing realms where new, unknown physics takes over. Perhaps there are exotic particles predicted by theories beyond the standard model that do not interact with the background radiation in the same way, allowing them to travel unscathed. Or maybe the Lorentz invariance, a cornerstone of Einstein's special relativity, is subtly violated at these incredible energies, meaning the rules of space and time themselves are different for the universe's most powerful particles. Each detection of a super GZK cosmic ray is a message from the absolute frontier. It tells us that our maps of fundamental physics are incomplete and that the cosmos is capable of generating energies and phenomena that defy our current laws. The paradox is not just a limit to be overcome, but a key waiting to unlock a deeper layer of reality. Gravity's cosmic magnifying glass is revealing a puzzle of its own. When astronomers use massive galaxy clusters as natural telescopes to peer at even more distant objects, they notice something strange. The way these clusters bend and distort the light from background galaxies, an effect called gravitational lensing, is often far more powerful than it should be. Based on the amount of visible stars and gas we can see, the gravity required to create such dramatic arcs and multiple images of a single galaxy is simply not there. It is as if you were looking at a person's shadow and found it was far larger and more distorted than the person themselves could possibly cast. This discrepancy is known as the lensing anomaly, and it forces a fundamental question upon us. Is this the definitive proof of dark matter's hidden hand, or is it a sign that our understanding of gravity itself is flawed? The dominant explanation points directly to dark matter. We already suspect that every galaxy is embedded within a vast, invisible halo of this mysterious substance. In a massive galaxy cluster, these individual halos overlap and merge, creating an immense, unseen scaffold of gravity. The lensing anomalies in this view are simply a direct map of this dark architecture. The distorted light is not following the visible galaxies, but tracing the contours of their true, hidden mass. We are finally seeing the shadow of the dark matter halo itself, yet a persistent group of scientists proposes a far more radical idea. What if there is no dark matter at all? Their theory, known as modified Newtonian dynamics or MUND, suggests that gravity behaves differently at the extremely low accelerations found in the outskirts of galaxies and within these vast clusters. Instead of weakening with distance according to Newton's and Einstein's laws, gravity gets a slight, unexpected boost. This modification to the rules could, in theory, explain the extra lensing without invoking any invisible particles. The lensing anomalies become the cosmic equivalent of a failed stress test, revealing a crack in our most fundamental theory of how the universe holds itself together. So, who is right? The debate is fierce, with each new observation scrutinized by both camps. Proponents of dark matter argue that their model, while still mysterious, can explain the lensing when sophisticated computer simulations are run. Advocates for modified gravity counter that their simpler formula naturally predicts the observed patterns without the need for a universe dominated by an unseen substance. The truth may ultimately lie in a more detailed map of the cosmos. By studying the subtle ways lensing distorts the shapes of millions of distant galaxies, we are creating a three-dimensional mass map of the universe. If dark matter is correct, this map will show a specific clumpy structure aligning with the laws of Einstein's relativity. If modified gravity is the answer, the map will reveal a different, smoother gravitational landscape. Each anomalous arc of light is more than a pretty picture. It is a data point in a grand experiment testing the very laws that govern the cosmos. Gravity remains the final rebel, the one fundamental force that refuses to join the quantum party. We have two magnificent, exquisitely successful theories that describe our universe. Einstein's general relativity paints gravity as the elegant curvature of spacetime itself, a cosmic canvas warped by mass and energy. It perfectly predicts the dance of planets, the bending of starlight, and the very expansion of the cosmos. Yet, in the subatomic realm, the rules are written by quantum mechanics, a world of probability, uncertainty, and discrete packets of energy. Here, particles flicker in and out of existence, and forces are carried by messenger particles. This framework has given us lasers, transistors, and the entire standard model of particle physics. The problem is that these two masterpieces are written in completely different languages, and when they try to speak to each other, the result is mathematical nonsense. At the heart of a black hole, or the moment of the Big Bang, where both immense gravity and tiny quantum scales meet, our equations break down into infinities, screaming that something profound is missing. This is the quantum gravity conundrum, the single greatest unsolved problem in theoretical physics. How do we weave the fabric of spacetime itself from the threads of the quantum world? The quest for an answer has spawned some of the most ambitious and mind-bending ideas in human history. One of the most prominent is string theory. It proposes a breathtakingly simple yet radical fix. What if the fundamental building blocks of the universe are not point-like particles, but unimaginably tiny, vibrating loops of energy? In this view, an electron is not a dot, but a string vibrating at one specific frequency. A quark is a string vibrating at another. Even the messenger particle for gravity, the hypothetical graviton, would be a string vibrating in just the right way. The different vibrations of these one-dimensional strings give rise to all the particles and forces we see, elegantly unifying them under a single theoretical roof. But this beauty comes at a cost. The mathematics of string theory only works if the universe has more than the three spatial dimensions and one time dimension we experience. It requires extra dimensions curled up into shapes so small that they are hidden from our perception. We are like ants crawling along a vast, thin garden hose, completely unaware that our one-dimensional path is actually wrapped around a second, microscopic dimension. A rival approach, loop quantum gravity, takes a different path. Instead of adding extra dimensions, it focuses on quantizing space and time themselves. Imagine the smooth, continuous fabric of spacetime is not smooth at all, but is woven from a network of unimaginably small, discrete loops. Space is not infinitely divisible. It has a fundamental grain, a smallest possible unit of volume, much like a digital photograph is made of individual pixels. Time, too, would advance in tiny, indivisible steps. In this theory, the universe is a constantly evolving web of these gravitational field lines, and the familiar smoothness of spacetime emerges from this underlying quantum structure, much like the smooth surface of a pond emerges from the frantic motion of countless water molecules. This provides a compelling picture of the Big Bang, suggesting it might not have been a singularity of infinite density, but a great bounce from a previous universe that had contracted. The most frustrating part of this grand search is the sheer difficulty of testing these ideas. The energy scales at which these quantum properties of gravity become apparent are 1 trillion times more powerful than what our largest particle colliders can achieve. We are trying to probe the universe's deepest secrets with tools that are, by comparison, impossibly blunt. How do you observe the vibration of a string or the loop in a spacetime pixel? Some hope lies in the faint echoes of the Big Bang. certain patterns in the cosmic microwave background might bear the imprint of these primordial quantum gravity effects. Others look to the eventual detection of gravitational waves from the very first instant of the universe, a signal that could carry the signature of spacetime's quantum origin. For now, these theories remain magnificent castles in the air, mathematical realms of stunning beauty and coherence, waiting for a single, solid piece of experimental data to anchor them to our reality. The conundrum leaves us with a humbling thought. We have mapped the cosmos and probed the atom, but the true nature of the stage upon which this entire cosmic drama plays out remains one of our greatest and most enduring mysteries. If a black hole is a cosmic drain from which nothing can escape, then its theoretical twin is a cosmic fountain. This is the white hole hypothesis, a region of spacetime that cannot be entered from the outside, only exited. It is the ultimate one-way door, but in reverse, spewing out matter and energy while barring any entry. The mathematics of general relativity allow for such an object, a perfect time reversal of a black hole. Where a black hole's event horizon is a point of no return, a white hole's horizon is a point of no admission. If you were to approach one, you would find yourself repelled, your clock slowing to a halt relative to the outside universe as you are pushed away by the sheer force of its outward explosion. It is a place where the universe violently refuses visitors. The most compelling idea for their existence lies in their connection to black holes. Some theories suggest that a black hole's interior might not end in a crushing singularity, but could instead bridge to a white hole in another part of the cosmos, or even in another universe entirely. This cosmic tunnel, an Einstein-Rosen bridge or wormhole, would link the infinite gravitational pull of the black hole to the infinite expulsion of the white hole. Matter falling into the black hole could, in theory, be hurled out of the white hole, a process called a bounce. This offers a less destructive fate for whatever is consumed, transforming a cosmic shredder into a potential gateway. Yet the stability of such a wormhole is highly questionable. It would likely pinch off instantly, preventing any actual passage. This leads to the most profound speculation of all. Could our entire universe be the result of a white hole? The Big Bang, in this view, was not a singularity in time, but the explosive output of a white hole, the final act of a black hole collapse in a parent universe. Our expanding cosmos would then be the interior of that white hole, a new reality born from the death of an old one. This idea forms the basis of the black hole cosmology hypothesis, suggesting a cyclical, or perhaps a branching, multiversal structure to existence. However, for all their mathematical elegance, white holes face a formidable problem, the second law of thermodynamics. They seem to violate the universal tendency toward disorder. A white hole, by spewing out ordered, low-entropy matter, would essentially be a machine that decreases entropy, a process that appears forbidden by the fundamental laws of physics. No such object has ever been observed, and most physicists consider them to be mathematical curiosities rather than physical realities. They are the perfect, symmetrical answers to equations that our asymmetric universe may have simply chosen to ignore. The white hole hypothesis ultimately forces us to ask if the universe values mathematical beauty over physical possibility, and whether the Big Bang was a unique beginning or just one eruption in an infinite chain of cosmic fountains. Even the reality you are experiencing right now might not be the final layer of the cosmos. This is the simulation argument, a hypothesis that suggests our entire universe, with all its galaxies, stars, and conscious beings, could be an artificial construct, a digital simulation running on a computer of unimaginable power in a higher-level reality. The idea, popularized by philosopher Nick Bostrom, rests on a logical trilemma. He proposes that at least one of three propositions must be true. First, almost all civilizations at our level of development go extinct before achieving the technological maturity to create simulations. Second, advanced civilizations have no interest in running vast numbers of simulations of their own ancestral past. Or third, we are almost certainly living in a simulation. If you reject the first two bleak options, the third becomes a startling possibility. If a single advanced civilization ever runs many such simulations, the number of simulated minds would vastly outnumber the base reality minds, making it statistically likely that any given conscious experience, including ours, is part of that simulated majority. The fine-tuning of our universe's physical constants provides another curious piece of circumstantial evidence. The fundamental forces and particle masses appear perfectly calibrated to allow for the existence of complex structures like stars, planets, and life. Alter the strength of gravity or the nuclear forces by even a tiny fraction, and atoms would not hold together, stars would not burn, and the cosmos would be barren. From one perspective, this fine-tuning points to a profound anthropic principle. From another, it could be interpreted as the careful parameter settings of a programmer who wanted their simulation to yield interesting results. Could we ever find proof? Some scientists suggest looking for potential glitches in the fabric of reality, shortcuts the programmers might have taken to conserve computational resources. These could manifest as subtle inconsistencies in the laws of physics at very high energies or tiny scales, much like seeing the pixels if you look closely enough at a digital screen. The observed limits in high-energy cosmic rays or odd quantum behaviors have even been proposed, though not proven, as potential candidates for such artifacts. Yet, the argument faces monumental scientific and philosophical objections. The computational power required to simulate every particle in a universe is a number beyond imagining, perhaps requiring more energy than exists in our entire cosmos. This leads critics to ask who, then, is simulating the simulators, creating an infinite regress. Furthermore, if consciousness is an emergent property of complex physical processes, simulating those processes would require replicating the entire universe down to the quantum level, which seems a pointless exercise for any advanced being. Is the simulation hypothesis a profound insight into our potential future, or is it simply a modern, digital repackaging of age-old philosophical questions about the nature of reality and a creator? It forces us to confront the ultimate question. If we are in a simulation, does that make the love you feel, the beauty of a sunset, or the mysteries of the cosmos any less real? Or does it simply mean that reality is far stranger and far more structured than we ever dared to dream? From the ghostly pull of the great attractor to the potential glitches of a simulated reality, we have journeyed across 35 of the cosmos's most profound secrets. Each of these enigmas, from the lithium problem in ancient stars to the phantom push of dark energy, is more than just an unanswered question. They are the very frontiers of human knowledge, the edges of our map where the dragons of ignorance still reign. This voyage reveals a universe that is not a cold, mechanical clockwork, but a living, breathing puzzle far stranger and more magnificent than our ancestors could have ever dreamed. The true engine of science is not a collection of settled facts, but this relentless, beautiful pursuit of the unknown. It is the courage to stare into the cosmic abyss and ask the next question, to build the next telescope, to dream the next impossible theory. So the next time you find yourself under a clear night sky, remember that you are not just looking at points of light. You are witnessing a vault of mysteries, each one a challenge to the curious human spirit. Let that wonder fuel you. Tell us in the comments which of these cosmic riddles captures your imagination the most. Is it the haunting silence of the Fermi Paradox, the chilling possibility of the Big Rip, or the ghostly hand of dark matter? The conversation is just beginning, and your curiosity is the most important tool we have.